Derivatives as slopes of tangent lines. Alright, in this first example, we're being asked to first sketch the graph of f of x equals x squared minus 4x. So we're not even going to look at the other part yet. This is a pre-cal warm up a little bit. We're going to go ahead and sketch a graph of x squared minus 4x. So the first thing I'm going to do is recognize that the y-intercept of this graph is 0, right? So this is x squared minus 4x plus 0. So I know I'm going to go through 0, 0. And then I want to try to find x-intercepts to this function. So that means I'm going to set the function x squared minus 4x equal to 0 and solve for x. So I have x times x minus 4 equals 0. I can set each piece equal to 0 because of my zero product property. So I get x equals 0 and x equals 4. Well, we knew x equals 0 was an x-intercept because it's a y-intercept. And then 4 is my other x-intercept. And at this point, I'm just going to go ahead and sketch an upward-facing parabola. So x squared minus 4x, we know that's a quadratic, so its graph is a parabola. Because the leading coefficient is positive, we know that this is an upward-facing parabola. So I don't know exactly what it looks like. I mean, I could plot points and figure it out, but I'm going to just sketch a pretty weird-looking parabola. Alright, so this is what my graph of f of x looks like. Just a sketch, right? So now I'm being asked to analytically find the values of x where the tangent line to f of x is horizontal. So it should say value or values where the tangent line to f of x is horizontal, because hopefully we can see that there's actually going to be only one location. And this is true for any quadratic. So a quadratic will sketch a parabola which has only one place of horizontal tangency. So on the graph, I can say, okay, well, there it is. But I want to do this analytically. I want to find the actual x value where this happens. So what I want you to know, what I want you to remember is that if the tangent line is horizontal, then the slope of the tangent line, I'm going to abbreviate this as tangent line, is 0. Alright, so we want to know, where is the tangent line horizontal? Well, the tangent line is horizontal if the slope of the tangent line is 0. And now we're going to turn this phrase, slope of the tangent line is 0, into some mathematical terminology. So slope of the tangent line is the derivative, and the function is f, so the derivative is f prime of x, is, in mathematics, is equals, and then of course 0 is the number 0. So when this question asks us to find the values of x where the tangent line to f of x is horizontal, it's definitely something where we're applying our knowledge. Well, tangent lines are horizontal, or lines are horizontal when their slopes are 0, and slopes of tangent lines means derivative, so I want to set the derivative equal to 0. So now that we have the power rule, we can go ahead and analytically find the derivative of f of x. So f prime of x is 2x minus 4. So I'm finding the derivative of each piece individually using the power rule. So the 2 comes to the front. I have 2x to the 1 minus, and then the derivative of 4x is just 4. So minus 4 equals 0. And then I'm going to solve for x. So I get 2x equals 4. And then I have x equals 2. So this is the actual value, and maybe we could have guessed that that might have been the value just based on our sketch, but that's never enough. So especially because we're told to analytically find the value where the tangent line is horizontal, we needed to understand the rationale that we have to set the derivative equal to 0. So notice we didn't plug in 0, which is what a lot of people do. That would be finding the slope of the tangent line over here, right? I wanted to find the x value, so I found out that 2 is exactly going to line up with my place of horizontal tangency. In this next example, we're asked to find all points on the graph of y equals x cubed minus 2x at which the slope of the tangent line is equal to 1. So now I want to know when the slope of the tangent line, and by this point, the immediate thing that needs to pop into your head is derivative. So I'm being asked to find when does the derivative equal 1. So the slope of the tangent line means f prime of x, or in this case y prime of x because the function's name is y. So y prime or f prime of x. When is this equal to 1? So what I'm solving is when does y prime of x equal 1? So I'm going to go ahead and take the derivative using the power rule. So I have 3x squared minus 2, so the power rule of each term, and then equals 1. And then I'm going to solve for x. So here I'm going to add the 2 to the other side, so I get 3x squared equals 3. And I can at this point solve this in one of two ways, and I'm going to show you both ways. So if I divide both sides by 3, I get x squared equals 1. So x equals plus or minus the square root of 1, which is both positive 1 and negative 1. So there are two values, two x values. Or from this point right here, I could have said 3x minus 3 equals 0. Could have factored out a 3 to get x squared minus 1 equals 0. And then I get 3 times x minus 1 times x plus 1 equals 0. And so I said each piece equal to 0. Well, 3 doesn't equal 0, so that doesn't make sense. But if I said x minus 1 equal to 0, I get 1. And x plus 1 equal to 0, I get my negative 1. So either way, this is a way to solve this particular quadratic equation. I get out the two x values, 1 and negative 1. But I underlined, as I read, find all points. Points are x and y coordinates. So in order to find the entire coordinate point, I'm going to have to take each x value and plug them into the original function to find the y value. So in other words, I need 1 y of 1, and then negative 1 y of negative 1. Alright, so if I plug in 1, I'm going to get 1 cubed, so 1 minus 2 times 1. So 1 minus 2 is negative 1. And if I plug in negative 1, I'm going to get negative 1 cubed, that's negative 1. And then minus 2 times negative 1, so it's going to be a plus 2. So I'm going to have negative 1 plus 2, so I'm going to get negative 1, 1. So these are my two coordinate point answers. So find all points on the graph of y equals x cubed minus 2x at which the slope of the tangent line is going to have a slope of 1. And now use a graphing calculator to sketch the graph and confirm your answer. So I've already gone ahead and pulled up that graph. So hopefully we can see here that at the point negative 1, 1, so right around here, if I were to draw a tangent line right there, I would have slope 1. And then at 1, negative 1, if I drew a tangent line, I would have slope 1 again. So, whoops, it disappeared, but that's okay. That was as long as we needed it for. So we can go ahead and sketch and confirm what we knew from that graph right there. That looked something like this. That at negative 1, 1 was something like this. If I were to draw a tangent line, that slope would be 1. And then same thing over here at 1, negative 1. If I were to draw a tangent line, the slope of that line would be 1. So at two different coordinate points, 1, negative 1, and negative 1, 1. Alright, in this next example, we want to find all values of x where the tangent lines to y equals x squared and y equals x cubed are parallel. So when we see the word parallel, we should automatically think that we want the same slopes. And now we want to know where the tangent lines to each of these graphs have the same slopes. So when we think about tangent lines to functions, we should think derivatives. So we want to know where the derivatives are equal, right? So same slopes as in equal slopes, so same as in equal. So we want to find the derivative of each of these functions and set them equal to each other to solve for those values of x. So my derivative here, y prime, is going to be 2x. and my derivative of this y function is going to be 3x squared. So now I'm going to set them equal to each other. So I have 2x equals 3x squared. And what I want you to remember right now is that we are not allowed to divide by x. So what we would need to do is set this equation equal to 0. So we have 0 equals 3x squared minus 2x. And then I would have to factor. So this is nice because they each have an x in common. So we have x, and then we have a 3x minus 2 left over. And now I have this product equal to 0, so I can set each piece equal to 0. So we have 3x minus 2 equal to 0. And adding the 2 and dividing by 3, I get 2/3 as one x value and 0 as the other x value. So again, the key is in recognizing I wanted the x values where the tangent lines to the graph of x squared and x cubed are parallel. So parallel meaning same slopes or equal slopes. Tangent lines, we should automatically be thinking derivatives, and especially since we care about slopes of tangent lines, we should definitely be thinking derivatives, and parallel means the same or equal. So we take the derivative of each function, set it equal to each other, and then use our strategies from previous classes to solve our quadratic equation. And in this last example, we're asked to find all values of x, or x values, where the tangent lines, again, we should be thinking derivatives, where tangent lines to y equals x squared and y equals 1 minus 3x are perpendicular. So if we want the perpendicular relationship, we want slopes to be opposite reciprocal. We want slopes to be opposite and reciprocal to each other. Reciprocal. So we want tangent line slopes to be opposite and reciprocal. So that means that I'm going to need to find the derivative of each of these functions. So y prime is 2x. So now this represents the slopes of tangent lines to the function x squared. And this derivative, which is just going to end up being -3, because the derivative of 1 is 0, the derivative of -3x is -3. So this represents the slope of the linear function here, 1 minus 3x. And if we want our tangent lines to be perpendicular, we need slopes of tangent lines to be opposite and reciprocal, that relationship. So here's one slope, 2x, and another slope is -3. So if we wanted these slopes to be parallel, as in the last example, or these lines to be parallel, we would set these equal to each other. But instead, we're going to need the slopes to be opposite and reciprocal of one another. So one of these slopes we're going to have to make opposite and reciprocal, and the easier one would be the -3. So we can turn that into 1/3 and set that equal to 2x. So again, perpendicular lines have slopes that are opposite reciprocal. So we're going to set 2x equal to 1/3, and then we're going to solve for x. So of course we can just divide both sides by 2. I'm going to think about that as multiplying by a half since I have a fraction on the other side. And I end up with x equals 1/6. I didn't have to choose -3 to make opposite reciprocal. I could have made this entire function opposite reciprocal. So I could have instead made this -1/2x. So negative makes it opposite, and then 1/2x makes it reciprocal, and set that equal to -3. And then of course the negatives, if we multiply both sides by negative, I end up with just 1/2x equals 3. So this is like 3/1. So I can cross multiply because this is an equation. So I can end up with 6x equals 1, and then divide both sides by 6, and there's my x equals 1/6. So doesn't matter which one you make opposite reciprocal, it's one or the other, so that they can have that relationship that one has slope m and the other has slope -1/m. So I'd have to take the whole derivative, so in this case it's all 2x, and put that whole thing on the bottom, so make it reciprocal 1 over that, and then also change its sign. So since it was positive, make it negative. So what's happening on the graph here, let's just close out with that understanding graphically, because we just solved it analytically, is we have the function x squared, which looks something like this. And then we have 1 minus 3x, so that has a y-intercept of 1 and a slope of negative 3. So down 1, 2, 3, down here at negative 2, and then over 1. So I don't know how straight of a line I'm going to be able to draw here, but I'm going to try. Alright, so here's my function, 1 minus 3x, and then here's my function x squared, and I want to know all values of x where the tangent lines to each of these functions are perpendicular. Well, the tangent line to a linear function is just that, just the linear function. So this 1 minus 3x, the tangent line to 1 minus 3x is 1 minus 3x. So notice I didn't say the derivative. The tangent line to 1 minus 3x is 1 minus 3x. And if I drew a tangent line at x equals 1 over 6, so that's going to be maybe right here, right here-ish. If I drew the tangent line to x squared at 1 over 6, doing a different color, it should cross that tangent line to y equals 1 minus 3x perpendicularly. So at 1 over 6, if I draw a tangent line, that tangent line will be perpendicular to 1 minus 3x, which is its own tangent line.